work and will hopefully find this helpful. Also, just notice it in Teams. I think I can't even see you when I'm in the slides, so you just have to scream if anything happens. I unfortunately can't see your reactions. In any case, so today I want to introduce you to causal graphs, which are a tool that I consider super helpful. So when I heard about them for the first time, there was in a workshop given by a sociologist, and I was like, hey, this is really cool. Why did nobody ever tell me that this existed? Because that would have been very helpful all along. Which leads me to the way that causal inference is taught in psychology, but also, I believe, in many other fields of research. So essentially, the message when we teach causal inference is that when you want to do causal inference, there are two options. The first one is you conduct a randomized experiment, and then actually the second option is there is no second option, so you just have to give up and ask different research questions. And then if you have advanced statistical training, you might learn things such as, oh, maybe you can control for covariates, maybe that helps somehow, or then you might learn about the possibilities of analyzing longitudinal data, but it's never quite clear whether that does anything about the problem with causal inference. So I believe this way of teaching causal inference is, first of all, bad for non-experimental research, because we all know that virtually all interesting research questions concern causality, because we usually understand the world in causal terms. We don't think in terms of correlations, but we think in terms of when I do this, then that will happen because of what I did. At the same time, we teach a norm that observational data are simply not admissible for causal inference. And then if you combine these two, if you're in a non-experimental field, where does that leave you? Like, either your research has to be boring, or somehow you need to deal with observational data, which is not technically allowed for drawing causal inferences. And so non-experimental psychology, and I'm also talking about my own field of research here, has come up with a specific type of workaround, and that is a specific style of writing an article. So it begins with a usual introduction that relies on a causal reading of the literature. So these people found that this affects that, and so on. And now the question arises, does this affect that? The methods and the results might be implicitly causal inferency, but never explicitly. So they never state, oh, we are going to identify the causal effect of this on that, but rather they might talk about, oh, X predicts Y even after accounting for these other variables. So maybe X is a risk factor for Y, whatever that is, or they might talk about longitudinal associations. And then again, we have a discussion, and that again makes only sense in terms of causality. So we're talking about the important implications of our findings. And then it's very important that you add that one paragraph that your study was only observational and no causal conclusions are warranted. And then you might nod to future either longitudinal or experimental studies that will surely fix this problem. We pointed out in a paper in 2020 that this type of article is very common. And now that I'm a senior editor at Psychological Science, I think it's actually even more prevalent than I thought. So this is like a standard template for observational research. And what is unsatisfying about this is that it is setting up a particular type of argumentative defense. So everything in your article screams X has a causal effect on Y. That is, in fact, why the article would be interesting in the first place, and that is why anybody is reading it at all. But then people might point out, oh, these data are observational, and that is essentially an attack. And at that moment, you have prepared a strategic retreat. Oh, no, we just said X predicts Y. Look, we even have that paragraph in there that states that correlation does not imply causation, and we are very well aware of that. And that is quite unsatisfying, academically speaking, because you're trying to criticize somebody for a claim they clearly implied, but they never made it explicitly. So it's kind of like you can't really have a productive argument in that manner. And now if you're an experimental researcher, you might think that this just proves that non-experimental research wasn't a good idea to begin with. But I actually also want to make the point that the way that we don't teach causal inference is also bad for all of research. Because even if you do experimental research, you will face certain causal inference problems or other inferential problems that can be productively rephrased as such. And to just give you a few examples, I'm going to talk about mediation and moderation analysis today, but then there are also topics such as missing data, generalization to different populations or different settings, and the whole topic of measurement, which can also be rephrased as a causal inference problem. And so I have some resources on the slides that you can follow up with, and the slides are on the OSF. You've probably already discovered the link there. So with that out of the way, so what should you know about causal inference? Let's talk about causal inference. And one distinction I want to make in the very beginning is that there are essentially two causal inference problems or issues. The first one is causal identification, and the second one is causal estimation. Causal identification is essentially the question, given your assumptions, if you needn't worry about sample size, if you observe the whole population, would you be able to estimate the causal effect of interest? So this is the first step, like would it be possible to recover the causal effect in principle? And then in the second step, you still have to estimate the causal effect. So the second step is about actually estimating the effect with the data you got, with your finite sample size, and with your assumptions. And today I'm going to strongly focus on the identification part. So I'm not actually going to talk about statistical models. And that is because I think the identification part is kind of underappreciated in research. So for example, I learned a lot about multi-level modeling, structural equation modeling, and so on, but very little about the assumptions under which these models identify the effects of interest. And the tool that I'm going to introduce to you are causal graphs, also referred to as directed acyclic graphs. So this is one particular causal inference framework developed by the computer scientist Judea Pearl. It's not the only framework for causal inference, so you will also sometimes encounter the potential outcomes framework, which uses a slightly different terminology, but is fully compatible. But I like the directed acyclic graphs approach because it is quite intuitive. So let me show to you how all of that works. So here's an example of the simplest possible causal graph you could draw. So we have two nodes here, educational attainment and income, and these nodes represent variables. So these could be any type of variable, quantitative, qualitative, one-dimensional, multi-dimensional, and so on. This could be anything. This could also be like one node, and that just says personality, but it means multiple things at once. And these two nodes are connected with an arrow. And these arrows represent causal effects. So what this essentially says is that educational attack could have or does have a causal effect on income. So this is what this arrow means. And the specific form of the causal effect actually does not interest at all here. So this is fully non-parametric. This could be a linear effect. It could be a non-linear effect. It could be an effect for half of the people, but not for the other half of the people. It just stands for some sort of causal effect for at least one person in our data. So we can use these causal graphs to encode our assumptions about how the various variables in the world are related. And now, for example, we could consider, well, we are thinking in terms of educational attainment and income. These could, for example, be affected by other factors, such as, to give you a simple example from my primer article from 2018, childhood intelligence. So that will probably affect how much education people attain, but it could also plausibly affect income. Then, of course, there isn't just childhood intelligence. There is also something like adult intelligence. So we can add that in here, and we add arrows, for example, to show that childhood intelligence does affect adult intelligence. That is just like a personality trait, so it's kind of stable, and we have that stability in there by adding that arrow. And then we also add an arrow, for example, from educational attainment on adult intelligence. So we actually have pretty nifty studies that use like very clever designs to identify like what is the return of education in terms of intelligence, and it does seem like there are small but reliable effects, so we can add these as well. And then, of course, adult intelligence might also affect income. So we are not just limited to including variables that we know. We might also be willing to add mystery causes. So this is an example. So this would be some variable u that could be unobserved. We just assume that there's something that affects both adult intelligence and income. And this is the DAG that we are going to work with for now, just to keep it simple as a toy example. So these graphs are called DAGs, or directed acyclic graphs, because first of all, they are directed. And that means that all the arrows point into a direction. We don't have any of these arrows that have two heads. Now, if you look closely at what we drew here, you will see that we essentially say adult intelligence and income are correlated for some unspecified reason, for some unspecified third variable. And this is essentially our replacement for a double-headed arrow. So this is essentially just expressing there's a correlation here due to other factors, but we don't know what these factors are. So we kind of do have like an undirected association in there. It's just encoded in a specific way. DAGs are called acyclic because there cannot be any cycles. So if you travel along the arrows, you can never end up at the same node. And this is essentially the notion that a variable cannot affect itself, or there's like a flow in time and causality only goes into one direction. So that makes some people think that, oh, but then we cannot model like bidirected associations, which are often quite plausible. But if you look at it a bit more closely, we actually do have this type of mutual causation in there, because we do say that childhood intelligence affects educational attainment, and educational attainment does in turn affect adult intelligence. So this is intelligence affecting itself, but it's over time. So we can encode like cyclic relationships, but we do need to unfold them over time so that the graph is acyclic again. And so these are just the basic. Now we have drawn such a DAG. And we are going to work with this now, and we are going to work here on a very strong assumption. We will return to the strong assumption in the very end and discuss what that all means. But we are going to assume that this is a causal directed acyclic graph. And that is essentially just meaning we haven't forgotten any important common causes in here. So for any pair of nodes in the graph, we have not forgotten any common cause in our depiction. And you will see that this is, of course, completely unrealistic in this scenario, but that makes it easier to work with the graph. So we are just going to roll it with now. Now, the canonical thing that one would want to do with such a graph is figure out whether and how to estimate an effect that one is interested in. And so here we are going to be interested in the total effect of educational attainment on income. And now we need to figure out what we actually need to do with our data to estimate that effect in observational data. And for that, we apply the so-called vector criterion. So there is a fully formalized, just like a set of rules that is fairly short, but I'm going to spell it out in a different manner, which I think is more intuitive. And so essentially what this vector criterion tells us is which variables do we need to statistically adjust for to identify the causal effect of interest. So which controls should we use and which variables should we probably ignore and not control for, because that could make things worse. And now the nice thing, now that we've drawn the graph, this is actually now just a strictly algorithmic procedure. So essentially we have our nodes, we know what we are interested in, and now we need to figure out any connection between the variables of interest, so any connection between educational attainment and income. And we can just read that off the graph. So for example, we can of course directly move from educational attainment to income, but we could also travel via childhood intelligence, or we could travel via adult intelligence. And then there's longer paths that we could take throughout the whole DAG because we have multiple nodes. So if we do that, we list out a number of paths. And now any of these paths could, first of all, introduce a correlation between educational attainment and income. And then that correlation could either be causal or non-causal. And now what we're going to try to figure out is whether any of these paths introduces a non-causal association. And then in the next step, we will try to get rid of those paths or block them so that we get rid of any non-causal association, so that anything that's left in the end is actually the causal effect of interest. And now figuring out for these short paths is probably easy for you, but for the longer ones, it gets a bit more tricky. And to make that easier, it helps breaking down paths into fundamental structures, how three variables can be connected. The first of these fundamental structures is a so-called chain. So we have an X that affects an M that affects a Y. And you probably know this type of structure as a mediation chain. And so what a mediation chain does, it does transmit an association, and that's a causal association actually. So X affects M affects Y, which also means that X affects Y. This is actually a causal effect here. And as you might also know from the context of mediation analysis, once we condition on the variable in the middle, for example, by statistically controlling for it, we block the transmission of the association here. I'm going to talk about that conditioning on a bit later because it's a fairly general term. For now, you can actually just substitute it with statistical control, which I assume is something that many of you know, like you just include that variable, for example, in your regression model or as a covariate in your ANCOVA model. So that's the first fundamental structure, transmits a causal association, which can be blocked by conditioning on the variable in the middle. The second structure is the so-called fork, and I think that one is also fairly well known. So we have a variable in the middle that is labeled C, and it affects both X and it affects Y. So this is also known as confounding or common cause confounding. And as you might all know, this induces an association. So in this structure, X and Y would become correlated, but that correlation is not causal. It's common cause confounding. It's due to a third variable. And again, in this scenario, conditioning on the variable in the middle, here C, blocks the transmission. And that's the whole idea behind third variable control. We statistically control for variables, and that removes non-causal associations. So that is the second building block. And now maybe the least intuitive one, or the least well-known, is the so-called inverted fork. So here we suddenly have two variables jointly affecting one. And this is kind of unintuitive. So first of all, such an inverted fork does not transmit any association by itself. So just because two variables jointly affect a third variable does not mean that they have anything to do with each other or are correlated in any manner. Now, the unintuitive thing is that once we do condition on the variable in the middle, for example, by statistically controlling for it, we actually open up the transmission of a non-causal association between the two variables that we have there. So X and Y would suddenly become correlated, conditional on the variable in the middle. And so this is a scenario in which third variable control introduces spurious or non-causal associations into your data. And this phenomenon is also known as collider bias. So I think collider bias is fairly unintuitive, but once you kind of know the structure that causes it, you start to see it everywhere. And to give you one example from my own field of research, personality research, so there are arguments about the association between conscientiousness, a personality trait, and IQ, so psychometric intelligence, or really any measure of cognitive ability. And so there are some studies that claim there's like no association, some studies that claim there might be even a small negative association. Now, we personality psychologists like to collect data that is easily available. And of course, that means that we will often collect data from college undergraduates, so psychology students. And what we might observe in such a college sample is actually a slightly negative association between the two, that with higher IQ, we find lower values for conscientiousness and vice versa. But now actually we have conditioned on a variable that is all our analysis are conditional on the person being in college, because we are only looking at college students. And so we are conditioning on a collider between the variables of interest. And now this is a simulated example, but it does tend to look like this in real data. So if you would look at the full sample here, not just at college students, at the whole population, you would actually observe that there is no association whatsoever. And so what is happening here is that by selecting for people who made it into college, you are introducing that negative association that is not itself causal in any manner. And so if you look at the panel on the right, you can probably kind of see what's going on here. So we get some people who make it into college by being very intelligent, and we have some people who make up for lower intelligence by being very high on conscientiousness. And then, of course, we also have people who are high on both who make it into college, but there just aren't that many of these because the variables aren't correlated. But one big part of the cloud is missing, and that is people who score lower on both variables. And so this is sufficient to induce a negative association here, which is purely spurious, but results from us conditioning on a collider. So that's one collider example. You can find more in, for example, that blog post that is linked there of mine, or many, many other papers on the topic, as this has now become a bit of a thing that people talk about collider bias. So returning to our example, now we have these three fundamental structures and know how they behave. And now we need to apply that to all the paths that we have spelled out. And if we now go through the paths, first of all, we have those that transmit non-causal associations and that need to be blocked. And these are essentially all paths that contain confounders, because the confounder is a source of a non-causal association. And then if there's, for example, a mediator in the chain, that will just get passed on. So both of these paths would be a problem. Both of these transmit non-causal associations. And we can only block the first one by conditioning on childhood intelligence. And for the second one, we could actually freely choose whether we condition on childhood intelligence or adult intelligence or both. There are also paths that transmit causal association and should thus not be blocked, because we are interested in the causal associations, so we wouldn't want to get rid of them actually. And one example is the mediated chain, where educational attainment affects adult intelligence, which in turn affects income. So this actually tells us, oh wait, we wouldn't want to control for adult intelligence because it's an outcome of education attainment, so we would remove part of the effect that we are interested in. And then the most complicated ones are the paths that are actually already blocked, but that would start transmitting non-causal associations if the collider they contained was conditioned on. And there are at least 3 of these in this particular scenario. So what you can see here is that all of these paths contain a collider. So we have a variable into which 2 arrows point. And that already means that the path cannot transmit any association on its own. The collider just blocks everything. However, if we conditioned on the collider, which happens to be adult intelligence in all examples here, then we would actually open up non-causal associations on the both sides of the collider, and we would actually start introducing non-causal associations. And of course, we don't want to do that. So if we take all of that together, we have seen that we have to control for childhood intelligence. We might consider controlling for adult intelligence, but then we see, oh, that removes part of the causal effect, and it actually introduces collider bias on top. So we shouldn't do that. And so returning to the graph, if we assume that this is the correct causal structure here, which is a big assumption, then it follows that conditioning on childhood intelligence is both sufficient and necessary to identify the causal effect of interest. So, and this was just a formal way to spell it all out. If you're used thinking about these things, it's just like, oh yeah, obviously there's just one confounder there. But often the situations get more complicated and then it's no longer quite as obvious. Now, I already told you that this conditioning is a bit of a more general thing. And this leads us to the whole topic of causal estimation, which is more of a side note. So there are different ways to condition on a variable to remove confounding. To give you some examples, one simple one would be stratification. So we simply split the sample into different subgroups and analyze these separately, and in the end, we combine the results again. We could also, for example, do regression adjustments. So we just add the variables into our regression model. We could use more complex weighting or matching approaches. So for example, you might have heard of propensity score matching or inverse probability weighting, which are also just means of conditioning on variables. And the important thing here is if your causal identification strategy was wrong, so if you didn't have the right confounders, then no amount of estimation can rescue you. And I know that there was, at least in personality psychology, like some time where people thought that propensity score matching somehow solved causal inference based on observational data, but it's just like a particularly nifty method to control for a lot of third variables. It does not change anything about the underlying logic, so you could still miss confounders and so on. And then still, if your causal identification strategy was right, you could still mess things up during the estimation stage. So it's not like the statistics wouldn't matter here. For example, your statistical adjustment might be insufficient because your model is misspecified, you miss nonlinear effects and so on, or you have measurement error in covariates and so on. So you do need to bother about both identification and estimation. It's just that maybe you have already more in your toolkit for the estimation part. So that was my brief introduction to DAGs, and now I want to apply them to slightly more complex situations. I'm not sure whether they are more interesting, but I think they are very relevant often in applied research. And the first one is mediation analysis. So to actually use an example for an intergroup contact research is, for example, you might have some randomized intergroup contact intervention, and then you want to know whether this intervention affects prejudice, but often you might actually be interested in specific mechanisms. So does the intervention work because it affects emotions, or does it work because it affects values, and so on. And so this is the basic setup. We're interested in a mediated indirect effect. And now I'm unfortunately returning to my own example simply so that it matches the text where you can read up on it. And so let's use a slightly sillier example. And the question whether eating ice cream as opposed to some sort of control food affects depressiveness. If you think about ice cream and depressiveness, there could, of course, be all sorts of confounders, such as, for example, age. My 5-year-old daughter eats a lot of ice cream, and she's a very cheerful person, but of course, it might also just be due to her age that she eats so much ice cream and is so cheerful. So for now, we are going to imagine that we are actually conducting a randomized study here. So we have participants, we make some of them eat ice cream, and we make some of them eat something else. But now, what that means is that unobserved factors can no longer affect who eats ice cream and who doesn't, because we're in charge and we decided, and if we randomize it, essentially nothing else can cause eating ice cream anymore. So we can delete that arrow. And if we delete that arrow, we don't need to worry about any unobserved factors down there anymore, because they cannot confound anything with eating ice cream. So we can just drop these, which is nice. But now in this hypothetical scenario, we are not just interested in the effect of eating ice cream on depressiveness. We actually have a theoretical model that eating ice cream gives people sensory pleasure, and that is in turn what reduces depressiveness, which I think substantively is not that implausible. It would be like a savoring or some mindfulness perspective here. And so what we do is we let people eat ice cream or something else, and then we actually assess how pleasant that experience was, and then we are interested in the effect of depressiveness. So we are interested in an indirect effect here, and that indirect effect actually has two parts: eating ice cream on sensory pleasure and sensory pleasure on depressiveness. And now to make causal claims here, and mediation claims are always causal claims because they are like about indirect effects, we need to actually make two causal claims. First of all, we need to have the causal effect of eating ice cream on sensory pleasure, and then we also need to know the causal effect of sensory pleasure on depressiveness. Now, the first part of this, the effect of eating ice cream on sensory pleasure, is no issue at all. We have randomized who gets to eat ice cream, so eating ice cream cannot be confounded with anything. So that's fine, we can estimate that effect. The more complicated part is the effect of sensory pleasure on depressiveness. Because in our design, we have not randomized sensory pleasure, we've only randomized ice cream. And so sensory pleasure is still like not randomized and could still be confounded in various ways. And to give you just one example, there could be some sort of positivity bias going on here. So people who give very positive assessments might say, oh yeah, this was super delicious, this was a great pleasure to eat this. And they might also be more likely to say like, no, I'm super cheerful, I'm not depressed at all. And now, if we do not take into account this confounder here, positivity bias, that will mean that we actually have a biased estimate of the effect of sensory pleasure on depressiveness. And if you combine that bias estimate with the other part, with the effect of eating ice cream on sensory pleasure, we still end up with an indirect effect that is in total biased. So if we wanted to get rid of that bias, we would need to adjust for positivity bias. And in general, if we do want to actually causally identify the indirect effect, we do need to adjust for any sort of confounding between the mediator and the outcome. So this is a big assumption in mediation analysis, that we have gotten rid of all of mediator outcome confounding, at least in the randomized case, where at least the treatment has been randomized. If the treatment wasn't randomized, there would be even more confounding to worry about. So we do need to worry about these confounders. But one thing one might wonder at that point is, well, maybe we can at least get the direct effect, right? Maybe we can at least get the effect of eating ice cream on depressiveness, holding constant sensory pleasure. So that's the idea, that maybe we can get the direct effect here. But now we need to reason about whether we can actually get that. And for that, we actually need to spell out all the paths we can travel here. So we can travel from eating ice cream to depressiveness via sensory pleasure. That is the mediated path of interest. And that is the one that we actually do have to block if we are interested in the direct effect, right? Because we want to remove anything that goes over the mediator. So we condition on the mediator here. And then there is a second way to travel from eating ice cream on depressiveness, and that is a more complicated path. That is, eating ice cream affects sensory pleasure, which is affected by positivity bias, which affects depressiveness. And now we already said, oh, we do need to condition on sensory pleasure because we want the direct effect. But if you look at the second path now, you will see that sensory pleasure is actually a collider between ice cream and positivity bias. So we have one of these situations where two variables point into a third one. And we already said, well, we do have to condition on that variable in the middle. And what that means is we just induce collider bias. It just always happens when you have these two arrows pointing in a thing and you condition on it. So what we have created now is a non-causal association between eating ice cream and positivity bias once we have conditioned on sensory pleasure. Now this might be confusing because you may think, oh, wait a second, but we randomized eating ice cream, right? So it cannot be confounded. But it's only unconfounded as long as we don't condition on any other variables. And if you condition on sensory pleasure, which is a so-called post-treatment variable, we destroy that randomization property. And one intuitive thing or way to think about that is, so imagine one group eats ice cream and the other group gets to drink sauerkraut juice. And then you only look at people who say that this was a super pleasant experience, best food they ever had. In the ice cream group, those will include a lot of people who don't have a very strong positivity bias because ice cream is very delicious. But in the sauerkraut group, this limits it to people who are really enthusiastic about sauerkraut juice, and that might be people who have some sort of positivity bias that they always say that things are amazing. So we've now induced a non-causal association between eating ice cream and positivity bias. And because the positivity bias in fact it also affects depressiveness, we have actually opened up a non-causal association between eating ice cream and depressiveness. So we need to condition on sensory pleasure to identify the direct effect, but once we do that, we actually induce a non-causal association. And now we would need to get rid of that non-causal association to actually estimate the direct effect. And to do so, we would once again need to condition on positivity bias. That's the only option we have here to remove that second non-causal path. And so we would once again have to assume that we've controlled for all mediator outcome confounders. So these confounders don't just bias the indirect effects, but they also bias the direct effects. So, which is all just to say, mediation analysis is a very hard causal inference task. And that holds even if the independent variable, which was eating ice cream, has been manipulated. And actually, it still kind of applies if the mediator has been manipulated as well. So that changes a couple of things. So fully experimental mediation analysis is like its own problem, but you still need strong assumptions to chain together the causal effects in the right manner. So I know some people have fully given up on mediation analysis, and it is a bit of a debate whenever it's brought up on social media. In any case, if you do want to do a mediation analysis, there are actually lots of incremental improvements that you can make to make your mediation claims more plausible. And that's mostly about taking into account mediator outcome confounders, adjusting for them in various ways, and also running sensitivity analyses, just to get a feel for how much confounding would be necessary to completely mess up your results. So there is a way forward here, but it's not the standard type of mediation analysis you usually get to see. And now, if we talk about mediation, it's quite natural to also talk about moderation. And so in case you don't know what moderation analysis is all about, that's about the idea that effects of an intervention vary between people or between other factors, and we are interested in how that is affected. So, for example, it might look something like this. You have a randomized intergroup contact intervention. You are interested in attitudes towards the other group and how they are affected by the intervention. But now, for example, you might have the idea, if you're a personality psychologist, that the effects of the intervention are actually affected by openness to experience. So maybe more open people profit more from that intervention. And so this depiction with the arrow on the arrow is not standard causal graphs terminology, because in a causal graph, you wouldn't actually need to indicate interactions because everything is fully non-parametric. So instead, we would actually just have an arrow from openness to experience into attitudes towards the other group. I still like arrows on arrows because I think people are used to it thanks to the process macro, and also it's kind of helpful to indicate like really what we have in mind here. So, but now we think about openness to experience, and this is not something we can manipulate. This is something we just measure. So the question arises, so could these claims here about moderation be somehow confounded? For example, we might claim that openness to experience moderates the effect of interest, but what if it's something else? For example, we know that gender and age might affect personality, so maybe these affect personality, and then maybe it is gender and age that confound the moderation analysis here. So maybe it's gender and age that affect how the intervention works. Now, you might naively just include gender and age in your model and notice that nothing happens and conclude that this is not confounded by gender or age. But one underappreciated fact is that if you're interested in an interaction and want to check whether it might be confounded, then you always need interaction controls. So here we would actually have to also include the interaction between the intervention and gender and age. And then when we do that, we might notice that the interaction term with openness to experience is no longer statistically significant. And in such a situation, the question is, okay, what does that mean? So does openness to experience moderate the effect of the intervention or not? And it turns out that the term moderation is used for two different scenarios. One that I would call a causal interaction, just to make it as clear as possible. And the other one is more a situation of correlated heterogeneity. So when you think of a causal interaction, it's a scenario in which the moderator causally affects the causal effect of the independent variable. So if we could change people's openness to experience, that would actually for them change the effect of the intervention. And in contrast, the correlated heterogeneity scenario is just one, okay, so the intervention has an effect and the magnitude of that effect is correlated with people's openness to experience. Right, so I already said that in the causal scenario, an intervention on the moderator changes the effect of the independent variable. And in the correlation scenario, it doesn't need to change anything. The moderator just happens to correlate with it. It doesn't mean that changing the moderator changes the effect of interest. If you have a causal interaction, there's actually always a symmetry. So in that scenario, an intervention on the independent variable of interest would actually also change the effect of the moderator. So if you're working with fully factorial designs, you might know this, that the interaction is always like both ways. It's just like sometimes easier to think it in one way than in the other, but it is usually symmetric, or it has to be symmetric. And this does not apply to the correlated heterogeneity scenario. So in that scenario, the independent variable does not need to correlate with the effect of the moderator. In fact, the moderator wouldn't need to have any effect to begin with. It could just be something that happens to be correlated with the effects of something else, but does not directly affect the outcome itself in any manner. So the question is, which of the two are you interested in? The causal interaction concerns the underlying causal web. And the correlated heterogeneity, well, it's a correlation. So it's not some underlying feature of the world, but rather something that comes out of your analysis. And for example, the magnitude of that correlated heterogeneity will depend on the other variables in the model. So there's not a true correlation between the moderator and the outcome. It depends on which other variables are in the model, just like there's no true correlate or association once there are more variables in the model. I do think it's very plausible to argue that we are most likely interested in causal interactions because we usually want to understand what is actually going on and how the interaction works and why that might vary between people. But correlated heterogeneity could still be interesting if you actually just want to predict how effects will turn out. So for example, you might want to identify groups for whom the intervention has a particularly large effect without speculating substantively why it's this particular variable. So you could just say, yeah, this tends to work well for people who belong to this and that group. We don't know why, but it's correlated with the effects. So if you want to make claims about a causal interaction, then you're doing causal inference. And so causal interaction analysis can be hard. It is a causal inference task if the independent variable has been manipulated, like we had it before in the randomized scenario, but the moderator has not been manipulated. So we still need to think about confounding between the moderator and the outcome, or between the moderator and other variables that modify the effects. However, here there is an easy way out, which does not apply to mediation analysis, and that is we could actually just randomize the moderator, and then we have a fully factorial experimental design, and then we can causally identify interactions. And that, of course, only works if we are interested in a moderator that can be randomized. And so I brought an example for you that is from a study that we conducted where the moderator could not be randomized. And that is actually happens to be contact research. So we conducted a randomized experiment in 182 Hungarian classrooms. And so at the beginning of the semester, the seating chart was just randomized. So students were reseated in a random manner. And at the end of the semester, it was just measured who befriended whom. So we have friendships as the outcome here. And of interest was the effect of being seated next to each other on the probability of a friendship. And we actually did find an effect. So in total, the friendship probability increased from 15% to 22%, or by 7 percentage points. Now, the more interesting question is whether this also works for dissimilar students. So does it also work if you set students next to each other who wouldn't usually befriend each other? And so what we did here is we calculated an index of similarity along through 3 dimensions, age, and 4, I think, 8, no, it was 3, sorry, gender, GPA, and ethnicity. And then what we do is we essentially evaluate the effect of the interaction at different values of similarity. And now you can see the results here. So in panel A, you see essentially just the marginal probabilities of a friendship, depending on the level of similarity and depending on whether students were seated next to each other. And then in panel B, you see the average marginal effects expressed in percentage points. So what you can see here is that for all three groups, there is an effect on the friendship probability, but you can also see that the effect is much larger for students with a high similarity. So for them, the friendship probability increases by many more percentage points. And now the thing is that we did not randomize similarity between students. They were just randomly reseated, but similarity was not something that we directly controlled. And so what we're actually just looking at is just the correlation between similarity and the effect of sitting next to each other on friendship. And so this could still be confounded in many ways. For example, it could be that the geographic region affects how similar students are on average in a classroom, which in turn might also affect how likely they are to befriend each other when they are sitting next to each other. And how plausible that confounding is also depends a bit on the variables that are involved in this interaction here. So for example, if you just think about similarity in terms of gender, so in gender match, is it two girls or two boys, or is it a mixed diet? Gender itself is often very plausibly exogenous unless the sample is highly selected, simply because biological sex is randomized at conception. And so if you just look at actually gender match, then it's much more plausible that this modification is actually also causal. And so I also brought you the results that just like split things down by gender. And what you can see here is that for mixed diets, so if it's a boy and a girl, so first of all, these are super unlikely to befriend each other. But then actually, if you sit them next to each other, they are slightly more likely to befriend each other, but it's still a very low probability. You might argue that this is a huge effect because it's so unlikely to begin with, but if you do express it in terms of like percentage points change, it's fairly small. And in contrast, if you have girls that you sit next to each other or boys, then the effect is quite big. And I think this is quite plausibly like a causal interaction here, even though we could not really like control the moderator of interest, but it's plausible that it is not confounded with anything. Okay, so that was a lot. There was a very quick introduction to causal graphs, to mediation analysis, and to moderation analysis from a causal perspective. And so I think one important thing to look back to, because in the beginning I said, okay, now we're going to work with the assumption that this is a causal graph. And the question is, isn't that assumption horribly unrealistic? And as it turns out, these assumptions are often quite unrealistic. It's often like the assumption that there are no additional confounders. And at the same time, we would be willing to say, oh, well, it could be like a multitude of causes affecting the variables that are not in the graph yet. So considering unrealistic assumptions, I think it's important to realize that there are no inferences without underlying assumptions. And I know that people like to think that their inferences don't rest on strong assumptions, but I think that's usually a situation where they haven't thought about them enough. So I often see people that report experimental findings and then they say X affects Y, but then if you look at the study, X is like some vignette study. So it's like the link to the actual cause of interest is extremely indirect. And so you might have something that is like in the study causally identified, but it has nothing to do with the causal effect of interest. And it's just because people don't really think about the assumptions that go into the inference here. So first of all, so this is just to say, yes, there will be assumptions and some of these might be unrealistic, and that just applies to all of science. The nice thing I think about an explicit causal inference framework is that the assumptions are more transparent because you need to have the assumptions encoded in the graph to figure out what you do in the next step. And so it's quite transparent, at least if you know how to read these graphs, that the assumptions are things like, oh, they assume that there is no link here, or they assume that there's only one way to travel from this variable to the other one. And this is, of course, something that you can then criticize in the next step. Another nice feature is that because this is all fully formalized, it allows for quantitative sensitivity analysis. So for example, you can say, well, maybe there's a mystery node here. How strong would its effects need to be to remove that other effect that I'm trying to estimate here? And that is all fully formalized in many different contexts, including mediation analysis. So these are all tools you can use to make your inferences a bit more plausible and more transparent. And a broader point here, I think that is important to keep in mind is pluralism in causal inference. So in general, causal inference is just about learning from data. And there are, of course, many different types of data. So these could be experimental, but also observational, but they could also just be qualitative data, which might also be interesting. And these different types of data are going to require different sets of assumptions. All of them will require some assumptions. They are just very different. And so this diversity of data and assumption can actually result in much better, more robust inferences. That is the idea of triangulation. However, I think one shouldn't be naive about that, because the triangulation doesn't work by just throwing more studies on the pile. It only works if the different studies actually rest on different assumptions that suffer from different biases and so on. So to really have this benefit of triangulation of multiple methods, you do need to be aware of the different assumptions that go into all the inferences. And for that, I really think you do need the causal inference framework to figure out whether these studies are making the same redundant assumptions or whether they are actually robust when taken together because they rest on different assumptions. And with that, I'd like to thank you for your attention, and I'm happy to answer all of your questions. And very glad that I can see faces again.